Students, welcome to our today's presentation. My name is Teacher Martin, and today we're going to look at the images formed by thin lenses. So basically, thin lenses are glasses that have the refracting surfaces, and we have two kinds of thin lenses. We have the convex lens or the converging lens, and we have the concave or the diverging lens. So for a convex lens, they are thick at the center, but for the concave lens, they are thick at the apex. So these properties give them different abilities to refract light. So for a convex lens, they converge light, while the concave lens, they diverge light. That's why they are called diverging lens. So before we look at the images formed by thin lenses, we are going to look at the three important rays. So we have several rays passing, but among those rays we have the three important rays that will help us locate the image, the position of the image, the size of the image formed, and whether the image is virtual or real. So the first ray is a ray of light passing parallel to the principal axis. So the principal axis is the one that is horizontal to the horizontal and perpendicular to the optical axis. I'm going to make a diagram very fast. For a convex lens, we have that is the optical axis, and the horizontal one is the principal axis. So we have a ray of light. As you can see, a ray of light is represented by an arrow, so you must indicate an arrow to show that it is a ray and not a line. So as the ray moves, it reaches at the optical axis where it is refracted, and when the ray is parallel to the principal axis, it is refracted and passes through the principal focus as shown in the diagram. So you can see the ray of light has passed through the principal focus. So this is one of the important rays that will help us locate the image formed by the lens. Not only the image, but also the position of the image. So for a concave lens, we have the optical axis and the principal axis. So the principal axis is horizontal, while the optical axis is vertical. So we have a ray of light that is parallel to the principal axis. The same case for convex lens. However, for a concave lens, it has a property that refracts the ray upwards, so it diverges the ray. That's why it's called diverging lens. So the ray diverges upwards. However, we cannot guess the position of this ray or the direction that this ray faces. So one of the important properties is that this ray should appear to be coming from the principal axis. So if we produce a line backwards, this line will join the principal focus. So the concave lens refracts or diverges the ray, but the refracted ray appears to be emerging from the principal focus, like that. If we produce a line backwards, you can see it is emerging from the principal focus, but in the real sense, it's not emerging from the principal focus. It is just a refracted ray that was passing parallel to the principal axis. So for convex lens, the ray passes through the principal focus, but for the concave lens, the ray appears to emerge from the principal focus after refraction. There is an error here. It's not refraction, it is a refraction. So that is one of the important rays. Let us look at the second one. So the second one is the ray of light passing or appearing to pass through the principal focus. So let me draw this diagram very fast so that you can see. For a convex lens, we have the principal axis, the horizontal one, and the optical axis, the vertical one. We have the principal focus, so capital F represents the principal focus. We have a ray of light that is passing. For a convex lens, the ray of light passes through the principal focus, so that is the ray that is passing through the principal focus. When that ray reaches the optical axis, it is refracted but its refraction is parallel to the principal axis. So this is the principal axis, and this ray is going to be refracted parallel to the principal axis as shown like that. So this ray is refracted parallel to the principal axis. So for a concave lens, let us see what happens. We have the optical axis and the principal axis as shown. We have a ray of light that is coming from a position from the tip of the object. When it reaches at the optical center, so as you can see this ray, if we produce a line, this ray is appearing to come from the principal focus, or is appearing to pass through the principal focus, but is not refracted through the principal focus. So if it for the case where it is appearing to pass through the principal focus, this ray of light is refracted parallel to the principal axis like that. So that is for the concave lens. If we produce a line like that, this ray of light will appear to be passing through the principal focus like that. So that is the second ray. So the ray is refracted parallel to the principal axis for both cases. That is for the convex lens and for the concave lens. Let us look at the third kind of ray that is important. Is the ray of light passing through the optical center. The optical center is a point where the principal focus, the principal axis and the optical axis meet. So I'm going to show you where the optical center is. So for the convex lens, so where they meet, where these two lines meet, this is the principal axis and this is the optical axis. Where these two lines meet is the optical center. So we have a ray of light that is passing through the optical axis. So this is the principal focus, as you can see. The distance from the optical center to the principal focus is the same. The same case appears behind the lens. So if we have a ray of light passing through the through the optical center, as you can see, this is the optical center. What happens is that there is no refraction. Refraction does not take place at this point. So this ray passes undeviated. So there is no refraction. So this ray passes undeviated. The same case applies to the concave lens. We have the principal axis and the optical axis. The center is the optical center. We have a ray of light passing. So this ray passes undeviated. So for both two cases, the ray of light passes undeviated or unrefracted. So that is the third kind of ray that is very important as much as locating the size, the position of the image is concerned. So let us look at the characteristics of images formed by convex lenses. So we have started with convex lenses, and there are a number of images formed by convex lens, different position, different sizes, based on the position of the object. So the first one is when the object is beyond 2f. Remember, f is the principal focus and 2f is twice the principal focus. So what happens when the object is located beyond 2f? That is beyond the principal focus. So let me draw this one very fast. So that is the principal axis, the optical axis, as we have said. That is the principal axis. We have the principal focus. That is the principal focus. So capital F represent the principal focus. Also on the other side, we have 2f. That is where 2f is located, and you can see I did not draw this one accurate, but it is twice the principal focus. So 2f is twice the principal focus. We also have another 2f on the other side. So we have a case where the object is beyond 2f. So we follow the 3 rays. We use 2 of them. If we can use 3 of them, it will work, but still, if we can use 2 of the rays, we will get the accurate position of the image. So the first ray is the ray that passes through the optical center, and we said this ray is not refracted, so this ray passes undeviated as shown in the drawing. So you can see this ray passes undeviated, and ensure that the ray is passing from the tip of the object, so and it passes through the optical center, so there is a straight line that is not deviated. Also, one ray cannot help us locate the image, so we use another extra ray. For this case, we are going to use a ray that is parallel to the principal axis, and we said earlier that this ray is refracted through the principal focus. So we have a ray like that. When it reaches at the optical axis, it is refracted. It is refracted, as you can see, it is refracted through the principal focus. And where they meet, where these two rays meet, is the tip of the image. So we have an image like that. So that is the image. So as you can see, the image is upside down. So the three things we do is that we see where the image is formed. As you can see, the image is formed between F and the 2F. Remember, the image is formed between F and 2F when the object is located beyond 2F. So also we can look at the size of the object. We can compare it with the size of the image. As you can see, the object is larger than the image, and when the image is small, we say the image is diminished. So in optics, we use the terms diminished and magnified. So when the image is smaller than the object, we say the image is diminished. And the image is real. As you can see, one of the rules is that when the image is real, we use full lines. So we use full lines. We'll see a case when the image is virtual, we'll be using broken line. So the image is real. The image is formed between F and 2F, as I have said. The image is inverted. As you can see, the image is upside down. Where there is an arrow is the tip of the object, and this tip is converted like that. So this is the tip of the image. So the image is inverted. So that is when the object is beyond 2F. Number 2, let us look at a case where the object is at 2F. The object is exactly at 2F. So where will be the position of the image? What will be the size of the image? Will the image be real or virtual? So that one we can use drawing to see. So that is the optical axis, the one that is vertical. That is the principal axis. We have F and 2F, that is F, and remember 2F is twice F. On the other side, we apply the same. We have F and 2F. We have now the object that is exactly at 2F. What will happen? So we just use two rays, and I propose that you'll be using the ray that is passing through the optical center and the ray that is parallel to the principal axis. So the first ray is the ray that passes through the principal through the optical center. As we said, this ray passes undeviated, so it is not refracted. Because one of the rays cannot help us locate the image, we use another ray, and we said we use the ray that is parallel to the principal axis. As you can see, this ray passes through the principal focus, so it's refracted and passes through the principal focus, and where they meet is the tip of the image. So we are going to draw that image. Our image is real, so you can see that is the image. As you can see, the image is located exactly at 2F, and if you look at the sizes of these images, they have the same size. So let us look at some of the characteristics. The image is real. The image is inverted. As you can see, it is upside down. The image is the same size as the object. So at 2F of the lens is the only position where the lens produces an image that is the same size as the object. Also the I've said it is inverted upside down. So this happens when the object is at 2f. The third one is when the object is between f and 2f. So what will happen when the object is between 2f and f? So let us do this diagram very fast. We have the principal focus and the 2f the same on this side. So this is our object. So we use the two rays as usual. The one is passing through the optical center, and we said it passes undeviated. The other one is parallel to the principal axis, and we say this one is refracted and passes through the principal focus. Where they meet is the tip of the image, and as you can see, our image is very large. So, and you can see that, you can observe that when we are moving towards the optical center, our image increases. So the image, as you can see, it is formed beyond 2f. So it's the opposite of when the object was at 2f. When the object was at 2f, the image was formed between 2f. So when the object has moved in between f and 2f, you can see our image is formed beyond f. And you can see the size. The image is magnified. It is bigger than the object. It is formed beyond 2f. It's real and it is inverted. You can see it is upside down. So the fourth one is when the object is at f. So we are going to look at the kind of image that is formed when the object is exactly at f along the principal axis. I'm going to make that drawing very fast. So we have the principal axis, we have the principal focus here and another principal focus. We are going to look at a case where the object is located exactly at f. So we use our two fundamental rays, and I said we can use the one that passes through the optical center and another ray that is parallel to the principal axis. The one that is parallel to the principal axis is refracted and passes through the principal focus. So the first one is the one that passes through the optical center, and this ray passes undeviated, as you can see. So there is no refraction along this ray. And the next important ray is the one that passes parallel to the principal axis, and this ray is refracted and passes through f and passes through the principal focus, as you can see. So the image is formed at infinity. So when the object is located at f, the image is formed at infinity. So you can look at the characteristics. One of the characteristics is that the image is inverted. Where it will be formed, it will be inverted. The image is real, formed at infinity, and it will be magnified. As you can see, where they will meet, the image will be much bigger because we will join it to the principal axis. So the image will be highly magnified and it will be real and inverted. So the next one is when the object is between f and the lens. So we are moving very close to the lens. So what will happen, or what will be, how will the image look like when the position is located between f and the lens along the the principal axis? So I'm going to make that drawing very fast. That is the object, this is the object, and so we have f and 2f, as you can see. So this is f, and the object is located between f and the optical center where the lens is located. So we're going to use our two rays, the one that passes through the optical center that is undeviated. As you can see, it passes undeviated, it's not refracted. The next ray is the one that is parallel to the principal axis. As we said, it is refracted and passes through the principal focus. So the image, as you can see, these rays have diverged at this point, meaning there is no possibility that the image is going to be formed on this side. So what will we do we can produce these lines backward. So in this case, we are going to have a virtual image, and the virtual image for a convex lens is formed when the object is located between F and the lens. So as we can see these rays, there is no image that can be formed beyond these lines. So but if we can look at these rays carefully backwards, they can converge at some point. So let us try to produce these lines backwards. So we have that one, we produce it backwards. I've used a different color so that you can be able to see. And also we produce that one. Where they meet will be the tip of our image. So if we produce these lines backwards, they will converge, but forward they cannot converge. So where they meet is the tip of the image, as you can see that one. So the image is formed, the image that is formed for this case is virtual. So let us look at some of the characteristics of this image. As we have said, it is virtual, and we said for virtual rays like these ones and virtual images we use broken lines. The image is erect. As you can see, the object is facing upwards and the image is also facing upwards. The image is magnified. As you can see, the object is very small, but the image is larger in size compared to the object. So the image is formed on the same side as the object. It's not formed behind the lens, it is formed in front of the lens, and it's formed beyond 2F. So that is the 5 main images that is formed along the principal axis of the convex lens. Now let us look at the characteristics of images formed by concave lens. We said concave diverges light. Light is refracted, but it's diverged away. So I'm going to draw this diagram, and all images of concave lens are diverged, and they have similar characteristics. So I'm going to use just one ray diagram. No, not ray diagram. I'm going to use one ray diagram to represent the kinds of images that are formed by concave lens. So that is the F and the 2F. So we have an object, and I've chosen randomly that our object be between F and 2F. We are going to use the two fundamental rays, the one that passes through the optical center, that passes undeviated, so it's not refracted. So that's one of the rays. And also we are going to use the ray that is parallel to the principal axis. Now for a concave lens, this ray is going to be refracted, but it will diverge upwards. However, the ray that has diverged upwards must appear as if it is coming from the principal focus. We said when it's parallel to the to the principal axis, the ray appears to emerge from the principal focus. So during your construction, make sure it is refracted, and its refraction, or the ray that is refracted, appears to come from the principal focus. So that is how the ray is refracted. So it's refracted upwards, and we can produce this line backwards. We will see that it appears to emerge from the principal focus as shown. So where this virtual ray of light meets the real ray of light that is passing through the optical center, where they meet will be the tip of our image. But the image formed is virtual. Now we have a virtual image because it has involved intersection of a virtual ray and a real ray. Where a virtual ray is involved, no real image can be formed. We can only form a virtual image. So the virtual image will be located at that point. So all the images formed by the concave lens have similar characteristics as shown. So the image will be virtual whether you locate the object anywhere along the principal axis. The image will be virtual. The image will be erect, it will be upright, and it will be diminished. So these characteristics cut across all the images formed by concave lens.